Well, hey, honors. Looks like we're doing the video lectures again. We're going to be talking today about the beginning part of Chapter 8. We're finally going to be talking about rotational motion. So here's our familiar notability, and hopefully this is recording properly, and well, we'll see where we get. But anyways, we need to start talking about rotational motion. So the basic premise is, up till now we've been describing moving in a linear sense. We've been in a linear sense meaning that our displacements have been somehow some straight line. We start here, we travel in a straight line to here. We've done it in both the x direction, I guess technically speaking, we've done it in the y direction too. So we've displaced this way. We've even done a combination of the two where we displaced in the x direction and the y direction, and we did something like this, where we launched off in that direction and we displaced like this. And when we did this, we were displacing in both the y direction and the x direction simultaneously. Now here we're involving a little bit of curved motion, so there's a little bit of curvature here, but we analyzed it in terms of an x displacement and a y displacement. We have since then actually got into rotational acceleration, the acceleration associated with changing direction. So the next logical thing to do is just look at motion in a rotational sense altogether. So we're going to stop looking at the linear version for a while, and we're going to start looking at motion in a circle. So let's see here. My cheesy attempt at a circle. So if we imagine we have some circle, and that would be the radius of the circle, and we're going to start right here, and we're going to walk around the circle that way, and we're going to finish right there. So I have gone through some displacement. I was here initially, I've gone to here, I have done some displacement. So the idea of our regular displacement isn't disappearing, we're just going to do something instead of. So we're still describing moving from point A to point B, we're just talking about now moving on a circle instead of in a straight line. The new way we're going to describe this displacement, that would be the radius as well, is going to be in terms of an angle. When I go from here to here, I've displaced that amount in the linear sense, but I've displaced that angle, so we could also describe that displacement in terms of that angle. And that angle would tell me what's called the angular displacement. The angular displacement. So that's how we're going to begin talking about rotational motion. We're going to start talking about our kinematics, things like displacement, in an angular sense. In other words, in terms of an angle that represents the displacement instead of the number of meters. So to be clear, that would be measured in some number of meters when I go from here to here. When I measure that angle, I'm going to be measuring in a unit called the radian. I hope all of you have heard of radians. I'm going to give you a quick refresher course. You know that angles can be measured in degrees, so if I start there and go all the way around, I have gone all the way around 360 degrees. Well, another unit for angles would be the radian. And the radian is defined as this. The radian is defined as that length divided by the radius of the circle you're traveling in. So the amount that I displace in our usual sense divided by the radius gives me the definition of a radian. Now, if I go all the way around, I've gone around 360 degrees. The length I've traveled is going to be the circumference of the circle. So delta x would be the circumference of the circle. The circumference of a circle is 2 pi radius, 2 pi r. Divided by r, which cancels, gives me 2 pi radians. So when I go all the way around a circle, I am traveling 2 pi radians. 360 degrees is the same as 2 pi radians. Different units, so you get a different numerical value, but in both cases we're describing this going all the way around. So our unit for angular displacement is going to be the radian. And we'll use the symbol delta x. I can't believe I just did that. We'll use the symbol delta theta, theta is our Greek letter for angle, to be our angular displacement. So we'll have delta theta as our displacement measured in radians, and remember, delta theta is just the angle represented by our regular displacement. Okay? So far so good, I hope. As we go through these problems, I just want you to keep in mind that we're going to talk about velocities, displacements, accelerations. We're going to talk about all the sort of things that we've been talking about, but now the motion is going to be something traveling in a circle. So we're going to be talking about something traveling in a circle, and we're going to adopt angular units. A very good reason for adopting these angular units is this. We've joked before about the Olympics, 400-yard run, Olympics. Gun goes off, go! Everyone starts running. And the gold medal goes to whoever gets to zero displacement first. Remember, in these units, displacement is final position minus initial position. Well, final position minus initial position, if I go exactly one lap, would be 0. That does not happen in angular units. In angular units, I'm at an initial position of 0. I go all the way around, I'm at a final position of 2 pi. I have actually displaced 2 pi radians. I could also say that I'm at 0 degrees, and I displaced 360 degrees. In either case, I do not have a displacement of 0 when I use this unit system. So that avoids that little joke we've been making. So there's a good reason for doing it this way. All right, next. If I go from here to here around my circle, I have traveled some length, so that's going to be associated with some number of meters. It's also associated with some angle, some number of radians. So going from there to there, it can be described with this, and we can describe it with this. And because we're describing the identical thing, there must be some way of equating these two. This and this must be related somehow. So let's put together a way of looking at how all these things relate. Let's have our, let's call it linear instead of regular. Let's have our linear version. Let's have our angular version. And let's see and we'll write down over here whatever the relationship between the two is. So for example, our linear version was displacement, and we measured that in meters. Our angular version is going to be angular displacement. The name's easy. Displacement, this version is called this plus what this is called. So if that's displacement, this one is angular displacement. Angular displacement is measured in radians. And there has to be some sort of relationship between these two. And we can get that relationship by looking at the definition of the radian. The radian is defined as displacement over radius. So if I do a little bit of algebra, displacement would equal regular displacement over radius. That means my regular displacement is equal to radius times theta. This gives me a perfectly good relationship between these two guys. And I'm going to rewrite that and make this cleaner here. So my displacement would just be the radius of the circle times my angular displacement. So if I know the angular displacement and my radius, I can figure out the linear displacement. If I walk from here to here and I walk pi radians, I can calculate pi radians times the radius would give me the distance I actually walked. So that'd be cool. Alright, the next thing to think about. We learned displacement, and last year we learned that the next thing we talked about was velocity. If I displace, it takes some amount of time. If I go from here to here, it takes some amount of time. And we described the relationship between displacement and time as being velocity. So we said that velocity was just displacement over time. And our units for that were the meter per second. Well, angular displacement over time would give us angular velocity. We're going to use the Greek letter omega. I know that looks like a W, but I swear it's the Greek letter omega. And omega will be the angular velocity. It's going to be displacement over time. Notice velocity is always displacement over time. Regular velocity is regular displacement over time. Angular velocity would be angular displacement over time. The units would be the radian and the time unit would be seconds. So instead of having meters per second, I have radians per second. And the relationship between the two. Well, if I were to take this and divide it by time, and then I'd have to divide both sides by time to make it fair. So if I divide both sides by time, it's fair. This piece right here, well, displacement over time is velocity. Angular displacement over time is angular velocity. And this gives us the relationship between velocity and angular velocity. Again, I'm going to erase this and tidy this up so it looks nicer. But the relationship would just be that velocity would equal radius times angular velocity. Maybe you're noticing a pattern in these relationships. At any rate, we've got velocity as displacement over time. If I change my velocity, we called that acceleration. And we said acceleration was changing velocity, and it took some amount of time, and our units would be meters per second squared for that. In the angular sense, I can change my angular velocity. I can go faster, 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 or go slower, slower, slower. But instead of describing it in a linear sense, going from here to here, faster, 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 we're talking about this. I'm going some angular velocity, and I'm going to go faster, 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 faster. That would be angular acceleration. We're going to use the Greek letter alpha. I sometimes call it fish for hopefully obvious reasons. If it's not obvious, alpha is kind of like a fish, just saying. Alright, so angular acceleration. Well, velocity over time is going to be acceleration, so angular acceleration is probably a change in angular velocity over time, and the units would be the radian per second squared. And the relationship between the two. Well, if I take velocity and divide it by time, and angular velocity and divide it by time, I would end up with this and this. So I could say that acceleration is just r alpha. And this gives us our three basic linear quantities that we already know, our new angular versions which are described exactly the same. We're still talking about displacement in time and velocity in time. It's just now our displacements are measured as an angle as opposed to a length. And the reason we do that is because we're describing something moving in a circle. Alright, well, let's see if there's anything else I should say about this. Yes, one more thing I should describe. We talk about coordinate systems. We talked about before when we're in one dimension, we would say to the right was the positive direction and to the left was the negative direction. So that way our vectors going this way were positive, our vectors going this way were negative. We need to have positive and negative in our coordinate system here. We're going to say that this direction, which is counterclockwise, we're going to call that the positive direction. Counterclockwise is the positive direction. Means if you have a positive angular velocity, that means you're going this way. If your angular velocity is negative, that means you're going this way. Cool, so counterclockwise will be our positive direction. And this is the relationship between all the pieces. And I think that's everything I need to say about this. Let's go have a look at a problem and we'll see what we can do. I'm saying let's look at a problem and I can't find the button. Oof. So flipping through your book, said that. Hey look, it's as if I looked at your book when I thought up that table. Anyway, you know where that is now. Let's do a problem on page 200. Let's do practice problem number 1. What is the angular displacement of each of the following hands of a clock in 1 hour? Some of you might not remember this, but a long time ago, clocks were actually not digital. They actually had hands that moved. They'd have a second hand, minute hand, and an hour hand. This one wants to know, as part A, how far the second hand will move in angular units in 1 hour. So let's figure that out. So we want to know the displacement of the second hand after 1 hour. Well, hopefully it makes sense, but the second hand of a clock will make 1 revolution. The second hand of a clock will make 1 revolution in 1 minute. Right? The second hand goes around every single minute, which means the second hand is going to make 60 revolutions in 1 hour. So in 1 hour, the displacement of the second hand will be 60 revolutions. Now, of course, we don't like the units of revolutions. We want the unit to be radians. So we know the displacement is going to be 60 revolutions, but what's that in radians? Well, let's convert units. 60 revolutions times, there are 2 pi radians in 1 revolution. If I go all the way around a circle, I have traveled 2 pi radians. I've also traveled 1 full revolution. Revolutions cancel, and that would give me 120 pi radians. So the angular displacement of the second hand in 1 hour, I did not mean to do that, in 1 hour is going to be 120 times pi radians. Problem is, that's actually not correct. We forgot a very important detail. The clock, the second hand, is going clockwise. Clockwise is not the positive direction. So we have to remember that as a vector, this would be the second hand goes counterclockwise, so it's negative 120. Alright, cool. Part B. They want us to do the same thing but with the minute hand. What is the angular displacement of the minute hand after 1 hour? So we want to know the displacement of the minute hand after 1 hour. Well, the minute hand is going to make 1 revolution in 1 hour. When the minute hand goes all the way around, that will mean it's taken 1 hour. Which means the displacement is going to equal 1 revolution. Now we don't like the units of revolution, so we'll convert, knowing that there are 2 pi radians in 1 revolution, which is going to be 2 pi radians. And of course the direction will be negative because the minute hand goes counterclockwise as well. It goes clockwise. Counterclockwise would be positive. Alright, so there's that one. Part C. We want to find the hour hand's displacement. So we want to find the displacement of the hour hand in 1 hour. Well, does it make sense, I hope, that the hour hand is going to make 1/12 of a revolution in 1 hour. In 12 hours, it'll go all the way around the clock once, so in 1 hour, it's going to go 1/12. We don't like the unit of revolutions, so we have to convert that to radians, remembering that there are 2 pi radians in 1 revolution, which will give us 2 pi over 12 radians, which reduces to 1/6 pi radians. Of course, you guys have a calculator, so you guys could actually calculate 1 divided by 6 multiplied by pi and come up with decimal numbers for this. I'm not using the calculator right now, but like on a test, you guys would use your calculator to calculate that out. Alright, I think that's pretty good. If you look at the Google Classroom, you'll see that it's been suggested that you now work on problems 2, 3, and 4 for the rest of the class period. Work on 2, 3, and 4, ask your questions, and let's get through it. Hope this video was okay, and well, we'll talk to you later. Bye.